summary and an outlook, which goes also beyond this system. And then hopefully we have some good discussion with the people attending. So, so what is the basic for this? I mean, I'm sitting here in Norway, in Bergen, in basically the old research center of Equinor. And for the Norwegian continental shelf, we have Norwegian Petroleum Directorate, who is responsible for oil and gas. And their technology strategy is basically threefold. The one is the next generation production systems on the right. Okay, this means interventions and capturing gases which are produced. In the middle, we see that we want to produce more. So challenging barrels. How do we get more out of the reservoir? And what concerns us is the first part. And so 1/3 of it is subsurface data acquisition. And it says here new seismic sources. It says ocean bottom seismic, reservoir surveillance. So what concerns us mostly is time-lapse seismic then, and dynamic data acquisition. So, and and basically this talk is about all of that. And to go back in time, the maturity of the Norwegian continental shelf, and I guess most of the basins we're exploiting at the moment, is in the stage that the reservoir size is decreasing, and that means also that we have smaller and smaller targets to find, and that the geology getting more and more complex. So, from benign anticlines in the early days, we didn't need much high sophisticated seismic to see them, and so the image quality was rather blurry. And over time, this image quality increases, and the methods we use increased. So from 2D via 3D, wide azimuth and multi-azimuth to full azimuth, and then ultimately to ocean bottom seismic. So why do we exactly need this ocean bottom seismic? We can see in some examples I copied here. So the first one, for example, is with ocean bottom seismic, we record immediately full azimuth recordings if we are driving around the sensor on the seabed, and the shooting vessel drives around it. And by that, we can stack better, and we get possibly the signal out of the noise, and we also get data back from shadow zones, which may appear, like, for example, at the edge of the salt. We also record multi-component data, and of course, you can get rock properties and fluid fills, possibly from these shear waves, but mainly in industry, we're actually using it to look beneath gas clouds, for example, right? So we're getting an image to actually where we need to drill in, if you see it here on the right side. We have a quieter environment on the seabed compared to definitely onshore, and the towed streamer, which pick up all the noise on the surface. So we also having the advantage of that, and we can therefore also do a lot of passive seismic recording if we want to do that. It's possibly also being more prominent in the future with sensors which are recording lower frequencies. And then at the end, in the last years, we see ultra-far offsets, and there you need something on the seabed offshore to record them. And therefore, we see also an interest in deploying at ultra-far offsets, which are beyond the streamer length. So why ocean bottom recordings again? So the reservoirs are getting smaller and hide in more complex geology. We need better images. That means we need more and better data. And therefore, we need to go on the ocean bottom to do the seismic. And there are a couple different methods out there to record this this data on the seabed, but the problem is that it's still too expensive. So it's more costs because we need additional vessels. Collecting the data takes more time. So first of all, also with deploying the sensors and then picking them up. And the sensors are usually expensive and too big. So so now next, I will just go through some of these methods. And I classify them as 5 main methods. So first we have the old method of just dropping something from the surface down to the seabed. Then we have another method where they drop basically streamers onto the seabed. And so that is ocean bottom cables, which I think don't exist that many anymore. Then we have the method where we place nodes on the seabed with an ROV. And also in the last decade or so, we see that we have these nodes on a rope. So for shallower water, we can easier deploy and recover the nodes from the seabed. And then we have some experiments where people are trying to build autonomous receivers, basically. So each of the receivers is basically one node. So if we look at the first method, this is basically too big because we need also an anchor for this. We just drop this from the sea surface, and we have a few of these sensors available because they're so big. And then we have an anchor which goes on the sea bottom, and it needs to be degradable. So we're leaving something behind on the seabed. Usually, if you have a system where you have an ROV, you again spend a lot of time finding these sensors and then picking them up without an anchor. But there are lots of let's say negative points to this method. Except if you would have so many that you would just have a coverage where you don't really care where they fall into position. The second method is these ocean bottom cables. So there are not many around of these, so they have a problem that they're picking up noises when they're rolling around on the seabed, or when you have an undulating seabed where they hang in the air and they don't record all the components. So you also have no cross-line receivers here, so you have a big gap usually. So I don't think we have too many of these left. And our best method is at the moment to put them out with an ROV. So, and then there are several methods which try to speed up these systems. But usually it's 2 ROVs on each side of the vessel, moving sensors out of a kind of cabinet, and deploying them also to the cross line. So this gives us also access to the system, so we can check, double check the nodes if they're working. We could collect data, we could check the coupling and things like that, but it's extremely expensive because we can only slowly move with this system, because for deep water, if you have 2 or 3 kilometer waters and you need all the cables and all the things on the seabed, and you can only move slowly with this system. But it gives us the best data, but you pay for it. Therefore, a cheaper method is then attaching them to a rope and just putting them on the seabed. And we will see these for shallow waters, and it's a cheap method which goes fast. But it has the problem also with the sampling. So it has a high sampling rate inline if you want, but it doesn't have any function of testing the sensor or or deploying something cross-line. And it's also limited for a certain water depth, so it doesn't work for very deep water. And then you have some experiments which maybe also be in limited numbers, receivers which are full autonomous receivers. So basically you have each receiver being an autonomous underwater vehicle. And these are big, right? So I mean, they need to be big because they need to they need to fight against the currents, and they have to drive down there and land and lift off again from the seabed. And therefore, also the buoyancy is a problem because they cannot be too heavy, right? Because they have to come back to the surface. And they are quite big, they are quite expensive, each of them, and I can see that these make really sense for basically undershooting over platforms or in very far offsets. So where you need just a limited numbers of receivers. But I don't think they are going to be in the numbers of 10,000s because also you would not have even space on a vessel for deploying them. So again, what is our principle? Actually, we want to produce something which is more efficient and has less impact. That means less environmental impact or HSE impact in general, and something which then gives us also better data. But OceanBottom acquisition is multiple times more expensive at the moment than standard streamer seismic. So we need to start looking at what can we do to reduce these costs. So, so one is to reduce the vessel costs. So we need to speed up the operation. We need to reduce the day rate of the vessel. So that means we don't really want to have ROVs on board, right? So they're expensive and they're slow. We don't need cables all the way down to 3 kilometers on the seabed because they can be entangled or they can slow down the whole process. And we want to basically increase the nodes per day we pull out. So we want to speed up the whole procedures. And for example, nodes on a rope is one of these solutions. Then we want to reduce the day rate of a vessel. So we basically, ideally, we would like to have vessels of opportunities with fewer crews and maybe even further to autonomous surface vessels. And then we want to reduce the equipment costs. So we want to standardize the equipment, make it smaller, and make it maybe modular so you can record several different things at the same time. So we want to have cheap components, mass production, more units per container, and then combine also equipment and surveys together. So if we want to miniaturize equipment, we also then could speed up the operations, right? So we can have more nodes per day also out. So this is connected. So this is the efficiency. On the other hand, we also want to reduce the environmental impact. So there will be increasing environmental restrictions, and this is endangering our license to operate. So we want to have environmentally friendlier shooting. So we want to have less sound emission levels, and that means we want to put less energy basically into the whole system while we're doing a survey. We want to have less sound pressure level. That means we want to have not a big burst of energy, and we don't want to send out any unused frequencies, which we don't need anyway, right? So we only want to send out the frequencies we want to send out. And then at the end, you want to also have fewer sail lines because that reduces your costs. So less sound emission levels means we want to have less shooting, and maybe more receivers is actually a solution for that, because if we have more receivers, we record more energy from below the seabed. And then we have less sound pressure level. So we we want to spread the energy. So we don't want to have one big bang. Maybe we want to have lots of little bangs or no bangs at all. So we want to reduce the harm to the environment. And then we've seen also we don't want any unused frequencies. So for example, E-source or low frequency sources, as several developments now have produced, they reduce the high frequency content, which is the most harmful one for life in the oceans. And at the end, we actually have marine vibrators, which can exactly determine which frequencies they want to vibrate in, and they will probably be commercial in about 2 years' time. So, and we want fewer saline. That means we want either gradient receivers or maybe gradient sources to reduce the environmental impact. So, and at the end, also we want to reduce any other HSE incidents. So we want to reduce the vessel days in total will mean we have fewer human incidents and less CO2 emissions. So what's the idea? Well, that's not the idea. So that's basically what we did previously, and some academics still do. I mean, these are seismological stations or seismometers, or maybe just geophones you drop overboard, and they can record for ultra long. So this is really not what we want to do. So we want to reduce the receiver size, and that's possible, for example, by using MEMS. And we've seen recently that there are developments in this direction. So, and we want to record in less time. That means we don't need a lot of batteries. So that would reduce also the receivers. And then we want to reduce the cost of the receiver. So as I said, mass produced, lower energy consumption, standardization, and simplification of the sensors. And we want to increase the quality of the receiver. So increased low frequency content, which comes maybe with the new MEMS also. And we want to secure the coupling on the seabed and reduce noise in general, which is any noise from a current to noise, internal noise, electronic noise, and things like this from the MEMS. So, and to reduce the size, I mean, over the times we've seen that the ocean bottom sensors getting smaller and smaller. So I just figured out all these sizes from the internet, and you see that's a dramatic drop in sizes of the receivers. And actually, I think we can actually go even further with these sizes. And there are some prototypes which are on MEMS base, which are really tiny. And this one, for example, would still record 2.5 months on the seabed. And maybe you don't need 2.5 months on the seabed if you have something like the Seahorse, like an AUV, which takes care of these sensors, and you have multiple vessels shooting an ocean bottom node survey. So the proposal here is, because the sensors are getting so small, that you actually have an AUV which carries these sensors and deploys them and recovers them. So you have a multi-purpose hovering AUV, which carries external swappable payloads. So this could be crates of these sensors, and an operation, an arm, which then can deploy or at least handle them when they need to be recovered. Of course, the AUVs has common sensors as usual AUVs, and it has a USB-L connection to the surface vessel. This could be the mother vessel, but it could be also some other forms, like, for example, autonomous surface vessels, or in areas where you have installations, you could have also be other communication systems to give the positions. So you have a semi-autonomous swap and recovery of these crates on the sides of these AUVs. So therefore, you need a standardized interface. Maybe also an easy battery swap for the AUV, and you may have some internal payload available anyway. So you could, for example, do some other surveys while you are deploying and recovering the nodes. So the nodes itself need to be in these crates. So you could have two standardized docks for external payloads on each side of these flat AUVs. And these interface with any external payload. And so now this is going into the business case. So that means if we are thinking of developing this type of thing only for one type of nodes and for seismic, then this will be rather expensive. So, but if you have a universal ocean bottom node, this could be also equipped with the side scanning sonar for inspections, for example, maintenance equipment, or additional batteries, for example. So these crates could then carry actually hundreds of seismic nodes in one run. So, the payload may have also autonomous functions. So it needs, for example, to control buoyancy. It needs that also, for example, if you're thinking about autonomous sample on the seabed with the arm. So like taking geological samples from seeps or maybe for seabed mining. And the AUV then can automatically exchange the external payloads. So if we are thinking of an AUV, which is maybe 3 meters long or something like that, and we're attaching two crates on it, this type of sensors could, for example, carry 800 ocean bottom nodes on one AUV. Even if it's smaller, it's quite a big number. And if we're looking at companies, some companies are driving around with 5 AUVs on their vessels. So if we're taking 5 AUVs, we have 4,000 ocean bottom nodes in one go. With 5 AUVs, we can deploy in one go on the seabed. So with the normal speed of an AUV, that means in 2 hours and 45 minutes, we have deployed 4,000 ocean bottom nodes on the seabed. In a very optimistic case. And even if you're thinking times 10, this is way faster than any other method. So and then you can swap the crates again. You can go out again, and let's say you have 3 runs with 5 AUVs. So you can deploy about 12,000 ocean bottom nodes in 10 hours. Or 28 or about 28,000 in a day. So these are extremely large numbers, which at the moment we have a maximum of something like a couple of thousand nodes, which we deploy in one survey, and it takes weeks to deploy them. So it would be pretty much a breakthrough if we even just go slightly in this direction with this speed and these numbers. So I said before, we want to have a multi-purpose hovering AUV, which carries external swappable payloads and operates a manipulator arm. So we could also add additional sensors to it. So for example, a GraphMag sensor, or we could have CO2 or hydrocarbon sniffers on board. So it needs a robust deployment and recovery system. And other parts of it, which basically all exist. All of these things exist already, just not in one system. The only thing which doesn't exist is a swappable payload. So external swappable payload would need to be developed and standardized. So if you go back to the 3 principles, then this system would be more efficient. We would have cheaper nodes, we have less vessel time, we have faster deployment and retrieval of the nodes, we have less impact. So we're faster, we're producing less CO2, We have less HSE events in general because we're staying less on the sea, and we are automating most of the operations. We have less seabed disturbance because we don't leave anything behind. So we're not dragging anything on the seabed. We don't leave any anchors there. And because we have now the possibilities to deploy 10,000s of nodes, we maybe can save some sail lines. So we have less shooting on the shooting vessels too. So overall, we can collect better data. So we have more and better receivers. So the MEM space is promising that we can get a better low frequency data. We can deploy denser and with equal coverage. And so we get a better image. And with a higher sampling rate, we also have a better image of the near surface. So any shallow gases or hazards which might be around. So if we make a list of all these different methods, then basically these AUV placed nodes basically tick all three boxes compared to the others, which have some advantages or the same advantages, but then missing one of the others or two. So the AUV basically would return to the deployment position using the USBL it has and grabs the sensor and place it in the crate. It returns with a full crate for possible swap and then identify necessary procedures and equipment. We still have to do that. We need to keep the sensors cheap and as passive as possible. So that means that in the seismic sense, we basically just want to have the cheapest possible sensor, which is not active, has no rotating things, has no anchor, has no buoyancy equipment or anything like that. And we want to have the AUV to be intelligent, right? So we want the AUV to be as intelligent as necessary. And that is basically the biggest task in the beginning. So we want to have an AUV which identifies sensors independently, which is the biggest hurdle because these sensors, they can be imprecise positioned. The sensor can move because of current or other things. They could be covered, so sand can fly over them, and they also can malfunction. So so this is one of the bigger issues we have, but I believe that it is rather easier task than when we think of self-driving cars in the street, where you have to take care of bicyclists and other things. So the proposal is also that we're not only using this for seismic, but we're using to allow for multiple businesses. So, and therefore we need this swappable payload on the outside. So, and that means we could do monitoring, for example, in seismic monitoring, but also gravity monitoring. We could do seep detections. We could monitor pipelines with the system. It could have extra batteries as payload or a side scanning sonar. It could do any form of subsea tasks and even interventions to, for example, detect valves on a pipeline and manipulate them with the manipulator arm. So this is the idea for the business case, so that you're not having one niche product. So you have a product which is standardized, has a standardized interface, and can then be used by different industries. Yeah, so it also then can perform several duties at the same time. So you could do different duties with the internal sensors and external equipment. And you need an artificial intelligence to basically run that and train it for each purpose. And you need basically then a computer system on board which you can reprogram. Yeah. So these are the main things for this. So in summary, I presented some idea, proposal for a more efficient system to deploy ocean bottom nodes. It allows also for multiple business opportunity and can deploy and recover thousands of ocean bottom nodes per day. So this reduces the vessel times and the overall costs for ocean bottom seismic surveys. We have less impact, so we're reducing the CO2 emissions, overall reduce the HSE risk, and we don't leave anything behind on the seabed. At the end, we have, due to the denser data, we have better data, and we can record multiple geophysical data parameters from the seabed. So this was the summary, and when we come to the outlook, I mean, here you see some of the development in Equinor and what we're working on also with other oil companies together. So, and all of these systems which you see here already exist and are tested. So this is a subsea communication system. You have docking stations for AUVs. You have AUVs inspecting and maintaining subsea installations. And you also have subsea docking stations to recharge AUVs, which was just, I think, yesterday tested offshore and worked out several times. So there are standards for this, and for example, the standard for this docking station could then also be used as a standard to extend that to an external payload. So we have these building blocks already from the facility guys. So the facility guys who are actually managing all the platforms in the subsea installations, they already have developed a lot of technologies which we can then build on for also geophysical purposes. And just to say the least, I mean, the things are changing. So and changes are coming, and of course, we have seen a lot of changes in the industry, and this we will see in the future, and in some of this in the near future, right? So we already seen PGS towing ultra wide sources, right? Recently, we have several developments of marine vibrators, which probably be commercial in 2 years' time. We have a development of AUVs as receivers. We've seen autonomous surface vessels, which autonomously work as in a swarm. So you could, for example, deploy marine vibrators on these autonomous surface vessels in the future. And here's the development idea from Equinor, which is a subsea shuttle, which is modular. It's actually 130 meters long, and its initially idea is to carry a CO2 also in winter times to sequestration sites, but it's modular, so you can basically equip it with anything. And if you have a hydrogen powered, you could actually think of using marine vibrators with these, or deploy sensors where the AUVs can swim out and reload their crates with sensors, things like that. And onshore, we have robots too. So onshore on platforms, we have inspection robots already being tested on the platforms. And why can they not be used onshore for deploying, for example, sensors in areas to reduce the risks to humans? So this was about it, and I hope we can have a good discussion now about the ideas, and maybe some I get some more inspiration. Thank you.